20 years ago, light field cameras captured our field's imagination by allowing, for the first time, a scene to be photographed once and computationally refocused later. In this work, we showed that a special type of single-photon camera allows computational refocusing, but in the time dimension, over an extreme range of timescales. That is, we can passively record light over an extended period of time and computationally create videos that focus on phenomena occurring at any timescale we want, from fractions of a second to fractions of a microsecond, all the way down to picoseconds. To achieve this, we simultaneously capture both very slow and ultra-fast variations in incident flux with a single camera. This represents a new regime of passive low-light imaging that generalizes conventional passive imaging techniques, which are limited to frame rates of a few kilohertz in low light due to the limited number of arriving photons, and active time-resolve imaging, which uses synchronization with a dedicated source, but only supports time spans that are within the sub-microsecond period of their sync, and can therefore only recover a limited range of intensity variations. Our regime can be thought of as representing the absolute limits of passive intensity imaging, where the flux incident at a pixel may contain temporal frequencies much higher than the rate of photon arrivals, and photons may be generated by any number of light sources, operating asynchronously at very different speeds, or even by motion in the scene. Here, the most we can ever expect a camera pixel to provide about light is the time of each and every photon detection, as measured by a clock that tracks real time with very high precision. So in this regime, incident flux at a pixel is not directly observable, but must be inferred from the asynchronous stream of monotonically increasing timestamps it outputs. And fortunately, even though free-running single-photon avalanche diodes have not been used this way, as far as we know, they can be configured to output such a data stream and enable this form of imaging. Now, to solve this inference problem, we introduce a theory that relates the sequence of monotonically increasing timestamps to the inner product of the unknown flux with any function we want. We show that simply summing the values of that function at the photon timestamps gives us a noisy estimate of this inner product, and we derive a noise model for inner products with the Fourier basis functions. We also show that modern SPADs can passively measure flux variations whose bandwidth is limited only by the timestamp resolution and can easily span DC to tens of gigahertz, which is orders of magnitude wider than was thought possible with intensity cameras of any kind. So to reconstruct flux, we scan the whole bandwidth by probing individual frequencies to identify those with statistically significant support in the timestamps. And unlike conventional cameras, where longer exposures cause blur, here, the longer the exposure, the more precisely we can reconstruct the time-varying flux. Finally, we'd like to emphasize that our approach correctly accounts for key non-idealities in single-photon imaging, such as non-negligible dead times and very low photon counts. We show multiple experimental demonstrations of passive ultra-wideband imaging, beginning with an experimental setup shown here. A single-photon avalanche diode observes a single point on this white surface. A light bulb is placed above the scene. Light from a 3 MHz pulsed laser is diffused onto the observed point, as is light from a 40 MHz pulsed laser. Finally, light from a raster scanning laser projector passes through a diffuser and onto the observed point. After reconstructing the flux function, we can visualize how it varies across timescales spanning roughly 9 orders of magnitude. At the scale of 1 second, we see the roughly 60 Hz refresh rate of the laser projector. Over tens of milliseconds, we can see the roughly 900 Hz flicker of the light bulb. Zooming in further reveals the time-varying modulation of the laser projector. At the scale of microseconds, we begin to see the pulses of light from the asynchronous lasers, and zooming in even further reveals the individual pulses from each laser. Finally, at the nanosecond scale, we can resolve an individual laser pulse. Our method also enables a type of non-line-of-sight imaging, where we recover the video shown by the laser projector from our observations of the diffuse raster scan signal. Finally, we demonstrate passive ultra-wideband videography in this scene of a spinning fan illuminated by laser pulses. Our passive imaging approach is more powerful than active transient imaging techniques, which fail to resolve the fan blades because they move at a different time scale than the strobed illumination. We can also visualize the appearance of this scene at many timescales. At kilohertz rates, we see the motion of the fan, and as we push to megahertz rates, we begin to see pulses of light from the laser. Approaching terahertz rates, we can visualize a propagating wavefront and the fan blades frozen in time. In conclusion, we believe that passive acquisition and processing of timestamp streams unlocks powerful new imaging capabilities that we are just beginning to explore for applications in computer vision and beyond.